This video is a discussion of the concepts involved in Chapter 13, which is the sampling distribution of a proportion and a mean, and also a discussion of Homework 6. There are two big ideas in this chapter. They are the central limit theorem for proportions and the central limit theorem for means. The first one, the central limit theorem for proportions, states that when the sample size n is large, then the sample proportions are normally distributed with a mean that's equal to the population proportion p and a standard deviation of the square root of p times 1 minus p over n. The sample size n has to be large enough to satisfy what we call the success and failure condition. That is, that both n times p and n times 1 minus p both have to be greater than or equal to the 10. The first several problems in Homework 6 deal with this central limit theorem to be confident. Problem number 2. Approximately 14% of children are nearsighted. A kindergarten has 197 students. Can the central limit theorem be applied to describe the sampling distribution of children who are nearsighted? Well, what we need to do is check the success and failure condition. Our n is 197. Our p is 0.14. So we compute n times p and n times 1 minus p, 27 and 169. They're both bigger than 10. So the answer is yes. Assume these children are typical of the population, and since the success and failure condition is met, we can use the central limit theorem. Part B, sketch the sampling model. What we need to do is find out what the mean and standard deviation is for this distribution. The proportion of nearsighted children, we're told, is 14%, or 0.14. That's the mean. The standard deviation is given by the formula in the central limit theorem. So for p, we substitute in 0.14, and for n, we substitute in 197. And being careful not to round off until the end, we get a standard deviation of 0.025. So what we want to do is sketch a normal distribution with a mean of 0.14 and a standard deviation of 0.025. If you go out 3 standard deviations on either side of the mean, remember, by the empirical rule, you capture 99.7% of the distribution. So we compute what the mean minus 3 standard deviations is, and the mean plus 3 standard deviations. So we're looking for a graph that has a mean of 0.14 and almost all of the sample proportions between 0.065 and 0.215. This would be the appropriate graph, centered at 0.14 and extending from 0.065 to 0.215. Next question, how many kindergarten students in this class might a school expect to be nearsighted? Well, to be on the safe side, they can expect anywhere from 0.065 to 0.215% of the children to be nearsighted. The sample size is 197. So on the low end, we take 6.5% of 197, get 12.8 or round to 13 students. On the high end, we take 21.5% of the 197 and get 42.4, which we round to 42 children. So they need to be prepared for anywhere between 13 children to 42. Problem 4. A new restaurant has 94 seats. Studies show that 79% of the customers demand a smoke-free area. How many seats should be in the non-smoking area to be very sure, and by very sure means to be 3 standard deviations away from the mean, of having enough seats there? Well, in order to find 3 standard deviations away from the mean, we need to determine the mean and the standard deviation. According to the central limit theorem, the mean is the true population proportion of 79%, and the standard deviation is the square root of p times 1 minus p over n, which, rounding to 3 places, is 0.042. So we're going to take the mean of 79% plus 3 times the standard deviation of 0.042 to come up with 0.916, about 92%. They need to set aside about 92% of their restaurant in order to accommodate the non-smoking people. How many seats in the restaurant? 94 seats. So that if we take that proportion of 94, we come up with 86 rounded up to 87 seats have to be for non-smoking patrons. So problems 1 through 4 deal with sample proportions. Problems 5, 6, and 7 deal with sample means. There is a corresponding central limit theorem for sample means. It says for large samples, and large samples in this case means samples of 30 or more observations, sample means are normally distributed with a mean equal to the population mean and a standard deviation equal to the population standard deviation over the square root of n. Problem 5. Carbon monoxide, or CO emissions, for a certain car varies with a mean of 3.1 and a standard deviation of 0.8. A company has 50 of these cars in its fleet. We're going to let Y bar represent the mean CO level of this company's fleet. Estimate the probability that the sample mean of these 50 cars is between 3.3 and 3.4. So this is a question not about an individual car, but the average of all 50 cars. So we need to calculate 2 z-scores. A z-score is what? It's a sample value minus a mean over a standard deviation. But our sample values are, in this case, sample means, 3.3 on one end and 3.4 on the other. The true mean is, population mean is 3.1. According to the central limit theorem, the standard deviation is the population standard deviation, 0.8, divided by the square root of n, which is 50. What I did is I computed both z-scores, being careful not to round off until the end. So to find the chance that the average is between 3.3 and 3.4 is equivalent to finding the probability that a z-score is between 1.768 and 2.652. We're going to use the standard online calculator. We're going to check off between, and the reported shaded area rounded to 3 places is 0.035. So there's about a 3.5% chance that the average CO emission of these 50 cars is between 3.3 and 3.4. Part B. Find the sample mean so that the chance that the sample mean exceeds this value is only 5%. Now we're going to be using the online calculator at the bottom of the screen. Recall from the first part of the problem that the mean of the sampling distribution is 3.1, and that the standard deviation is the population standard deviation over the square root of 50, which is about a 0.113. So we're trying to find the sample mean above which only 5% of the distribution lies. So we're going to ask our standard normal calculator to find the z-score above which there's only an area of 5%. The calculator reports that that z-score is 1.6449. So we're going to take our formula for our z-score and we're going to solve it for y bar. Y bar becomes z standard deviation plus the mean. The z is 1.6449. The standard deviation we just calculated, and we're going to leave it to several decimal places. The mean is 3.1. The computation yields a sample mean of 3.3 rounded to 1 decimal place. What this says is there's a 5% chance that the mean CO emissions of this fleet is 3.3 or more. Problem 7. A waiter believes the distribution of his tips has a model that is slightly skewed to the left, with a mean of $15.40 and a standard deviation of $5.20. He usually waits on 40 parties over the course of a weekend of work. Estimate the probability that he earns at least $700 on the weekend. What they're asking is, what's the chance that his tips from 40 parties exceeds $700? So for him to make $700 when he serves 40 parties, if we divide 700 by 40, that means that the average or mean tip per party must be $17.50. So we're going to rephrase the question to say, what is the probability that the mean tips for his weekend exceeds $7.50? Now, interestingly enough, even though the distribution of tips is skewed to the left, the distribution of average tips is approximately normal because the sample size exceeds 30. It's 40. So we're going to use the central limit theorem and compute a z-score corresponding to his getting $17.50 for a tip on a particular party. $17.50 minus his average tip of $15.40 divided by the standard deviation, which according to the central limit theorem is the population standard deviation over the square root of the sample size, is 2.55. So we're looking for, he wants to make more than $17.50. We're looking for the area above 2.55, which is pretty small. Rounded to 4 places, it's a 0.0554, which is less than 1%. So there's actually a very small probability that the average tips for the weekend is going to be greater than $17.50. Next question. Let's turn things around. Let's now find the tips of the best 5% of such weekends. We're going to use the normal calculator on the bottom of the screen. We want a z-score that chops off the top 5%, so above. We find that our z-score, and you can look back to the previous problem for an explanation of this, our z-score is 1.6449. We're going to multiply by the standard deviation, population standard deviation over the square root of the sample size. We're going to add our population mean, $15.40, and this turns out to be $16.75. Okay, that's per party, but he's going to wait on 40 parties in the course of the weekend. So the best 5% of the weekends, he's going to make $670 or more.